I'm Yongyang. You can call me YY. So this is a joint work with some people here. Is Buzz Blocker and Tassos and Kanjad. So I'm a PI and associate professor in Ohio State University. So the team includes a lot of different university people here. So the question here is we want to answer what is our optimal policies to climate change in a dynamic stochastic economy. So first you think why a stupid economist needed to use a supercomputer, right? So in fact, many economists have the same question, say why they need to use the supercomputers. So here, first we need to understand why we need to worry about climate change now. Why we say just wait here, wait and see, or after 10 years, see what will happen, and we do our action at that time. So there's one key problem here, because global warming is a kind of a time lag. You know, if we say temperature now is say 5 degrees higher, so if we want to cool it down, sorry, you cannot cool it down in 1 year or 2 years or 3 years. You will take hundreds of years to cool it down. So this time lag, so it tells us we need to act now instead to, okay, we wait. So that's one thing. So then another thing is, so why we need to say policy, we need to act, we need to act now, then how to act it? So say we impose some carbon tax. So then the question is, yes, how large? Usually our president doesn't like to impose that. So then how large? So when we started? So these kind of questions are, you need to think about the long-term costs, you know. So you stand here, you need to think future. So future is not just 1 year, 2 years, 100 years, maybe 500 years, maybe even longer. So these we need to model it in a dynamic system, right? So we need to have this many years future in our projection. Then the question is, yes, can we really predict it well? Sorry, economy, climate, they are very complicated systems. We have no way to predict it so well. So the future projection, there are so much uncertainties there. So that means it's very stochastic. So this is a dynamic stochastic system. So then we need to say what's our optimal decision here. So that's the optimal decision problem. So then how to get an optimal solution? So the system is very complicated, so it needs a lot of data variables to represent this system. So these dynamic stochastic themes make it a very computational challenge. So that's why we need a supercomputer, like Blue Waters. So then in the current literature, people just talking about global warming. So they always use one pass, say, average the global temperature. But in reality, in climate, we know temperature, say, if we say global warming is 1 degree higher, that doesn't mean everywhere is 1 degree higher. So in the tropical area, if it's 1 degree higher, then in the North Pole, it will have about 2 degrees higher. So this is different. So then the question is, when we say global warming, the temperature, they create some damages. Did they really create damages? How much? So it depends on the spatial place, depends on locations. Tropical area nowadays say, oh, it's already high, so if you say 1 degree high, oh, that will create a lot of challenges. So we'll have a huge damage there because they cannot survive maybe. But in the North Pole, if 1 degree higher, you know, particularly in Russia, if 1 degree higher, oh, they will be happy maybe, you know, because then maybe some place maybe warmer, so they can plant some new plants, corns there. So some places may be beneficial, some places are not. But so it's so very complicated. But in some other places, yes, North Pole is higher degree than it means the Arctic sea ice, they will lose faster. So that means what? And also means Greenland ice sheet and West Antarctic ice sheets, they may melt down quickly. And this leads to what? Sea level rise. So sea level rise, many cities could be under the water. San Francisco could be underwater. New York could be underwater. So huge damage there. Then other things, yeah. North Pole is they are melting, so that means permafrost is thawing. So it means it will change their ecosystems and some damage in infrastructure, and also a big issue. Greenhouse gases stored in permafrost could be released. How much there? It's about 1,700 gigaton. So is it a big number or not? Current carbon in the atmosphere is 800. So there's one standard number. Say if we double this size, it will be about 3 degrees higher. So now 1,700 is not double, it's triple. So 6 degrees higher. So this will create a huge damage. But from my analysis, some good news is they are releasing it not so quickly, so we can control it. And increase the frequencies of extreme weather events, and also some tipping points. So tipping points here is mean once something happen, it's kind of create some irreversible changes. So you are switching your states from one state to another state, and it will never come back. Just like ice sheet melt. After it melts, you say, let it come back. No way. It will take 1 million years to come back. Ice sheet, once it melts, it's very hard to get frozen like that again. So here we create a dynamic stochastic model here. So we need to, so this is a model here. So first, because we wanted to say this temperature, we need to have a spatial pattern, but also economically, we also needed to think about it. So economic in the north part, most countries, they are rich. But in the tropical area, like Africa, most countries, they are poor. Poor countries, they are also more vulnerable to climate change than the rich people. And these rich countries, they are kind of, Russia, they are kind of beneficial from this climate change, and then Africa, they are not. So in economy system, it's very interesting to separate this into two parts, north region and the tropical south region. Then they have economic production, so they have emissions. So these carbon emissions into carbon in the atmosphere, so we have 3 levels to represent this carbon concentration. So upper ocean and deeper ocean, they are absorbing some carbon. And then we have 2 temperature levels in, 3 temperature levels. One is oceanic temperature, then 2 levels. One is in the north region, another is in the tropical south region. So then we say this atmospheric temperature will create some damages, okay? And also they may lead to some sea level rise. So sea level rise create another source of damage, and some climate tipping points, they create a third source of damages. So these damages will influence this production. So then what we can do here, mitigation. So we can try to mitigate the carbon emissions. Second, adaptation. So we can try to adapt to these damages and these sea levels. So adapt to damages, for example, we buy some air conditioners. And then we have consumption, say we may want to consume a little, then for the future, save for future. So investment between them, so maybe we want to invest some money from this region to another region. Okay, So this is a dynamic stochastic system, in fact. So every time they are changing, and this is a stochastic climate tipping, we don't know. So the data variables here is a totally more than 10 data variables. So in mathematics, it means you are solving problems like PDE with 10 data variables. And also more complicated than PDE because we need to have optimal decision here. So we call it HJB equation. So luckily, we don't need to the time step size could be small. So not so small, could be say annually time step size. Because in policy world, we cannot set our policy every second. We have to say, okay, every year we may change our policy. So that's our time step size. So then we solve 500 years horizon, so it becomes solvable in supercomputer. So here's some mathematics. So we say tipping points, they are, have some probability, so dependent on the temperature. So this is a Poisson process. So if we say temperature is less than 1 degree, then we assume we'll have no tipping point. But if it's bigger than 1, then higher temperature will have a higher tipping probability. And so this transition law, so here is 0, 1, so that means it's irreversible. So once you go to the second state, then it will be not reversible. So this will take some time. You know, ice should melt. It will not melt in 1 year. It will melt, to say, once it collapses, it will take some, say, 10 years, 50, 100 years to completely melt it. So that takes some time, but once you collect, it will cannot merge them together. So here's our transition law. So we have some tipping data, next data depend on the today's data with some increment, and also have some maximum damage level there. So it depends on if your tipping has already happened or not. So we use the AMOC as our representative tipping element. So here's the net output. So we can see, so this output, this YG is a gross output, so without any damages. But then you say after you have some tipping, so you may have some damage from tipping, and you have some damage from sea level rise, and some damage from temperature, directly temperature increase. And we can adapt it, so these have adaptation to reduce the damage. So, you know, people in economics, you need to think very differently. So they may have risk aversion, right? So, but they also, you know, have some we call the intertemporal elasticity of substitution. So like today's consumption, tomorrow's consumption, do you think they are equivalent? Or this year, next year, your consumption, your weight are same? Or your consumption, your next generation's consumption, do you weight same? So you even want to weight more for your next generation? So this we call the elasticity of intertemporal elasticity of substitution. So these things will influence your decisions. So here we say we have use this a lot of mathematics here. So here we have data variables. So we have 10 dimensional and 10 continuous data variables, 1 binary discrete. And we have 8 decision variables here. So we want to solve this problem, but this is a Bellman equation. So this T is from 1 to 500. So solving it is very time consuming, so we need to use parallelization. So it's in fact just backward induction. So here in parallel is in this maximization step here. So at every node at each time, so it can be parallel. So solving this, so our one typical example, we need to solve 2 billion optimization problems. And if we use 3,000 cores, it takes 3 hours. But if we don't have a supercomputer, it takes 1 year. The largest example, 372 billion of optimization problems. We use 84,000 cores, takes 8 hours in blue waters. Otherwise, it took 77 years. I cannot live so long, so I'm so happy to use blue water. So there are some results. So we say social cost in the north region. So we say if we incorporate the tippings and the damage, social cost increase significantly from here to here. So the social cost of carbon is measure the long-term costs of emissions at today. So 1 ton of emissions at today. So these are our tipping damages. So like I say, in 1% quantile, it happens here, starting from here, and damage is increasing. Then the top damage level is 15%. And if we ignore this polar amplification, so we can see there are some bias here. So this solid line means we consider the polar amplification. So this dashed line, we ignore the polar amplification. So we can see they have some bias here. We need to take into account this polar amplification. Also, we can see the temperature in the north region. Temperature with the polar amplification, temperature will be higher, and in the tropical region will be lower. So their difference is also very big. You can see that. So also adaptation. So in the north region, so with the polar amplification, so we have high adaptation rate, and tropical we have lower. Yeah. And so also you can see the sensitivity analysis. We are saying a lot of parameters. We really don't know. So this IES, this risk aversion, and also some say, okay, this is the damage hazard rate here, so then risk aversion. So we can see it have very wide ranges here from hundreds to up to 400, 400 or 500. So using blue waters, we have a lot of publications here. So the recent one is in JPE. So this is the top journal in economics. And then other is in the operations research in nature climate change, and PNAS. And also a lot of working papers here. So the one impact is a White House report in 2014. They incorporated our JPE papers conclusions, saying the high social cost of carbon can be justified without assuming the possibility of catastrophic events. So we thank Blue Waters, and also thank NSF. And so here's we can see the regional SCC stochastic programs. We can solve them, and it depends on the ranges of risk aversion, this IES, and also welfare weights. So I forgot to mention that. So welfare weights here means your north region and the tropical region. So do you think they are equal weights? Every people are equal, but these people, in fact, they don't want to be equal. So somehow you need to say adjust it. So then we find that ignoring this polar amplification, so will lead to a lot of biases. And so we also see the sea level rise, endogenous sea level rise is very important. We need to incorporate it. And also the welfare weights are very important. So when you do just a global average, just means you are assuming every people are equal. So you want to, you want to invest a lot of money to the Africa people, but people are selfish, so they don't want to invest too much money there. So these are a lot of things that we can see. Yeah, thank you very much.